There is a mystery at the heart of our universe. A puzzle that so far no one has been able to solve.
It's too weird.
Welcome to my world.
If we can solve this mystery, it will have profound consequences for all of us. That mystery is why mathematical rules and patterns seem to infiltrate pretty much everything in the world around us. Many people have, in fact, described maths as the underlying language of the universe. But how did it get there? Even after thousands of years, this question causes controversy. We still can't agree on what maths actually is or where it comes from. Is it something that's invented, like a language, or is it something that we have merely discovered?
I think discovered.
Invented.
It's both.
I have no idea.
Oh my God!
Why does any of this matter? Well, maths underpins just about everything in our modern world. From computers and mobile phones to our understanding of human biology and our place in the universe. My name is Hanom Fraj and I'm a mathematician. In this series, I will explore how the greatest thinkers in history have tried to explain the origins of maths' extraordinary power.
You've ruined his equation.
I'm going to look at how, in ancient times, our ancestors thought maths was a gift from the gods. How in the 17th and 18th centuries, we invented new mathematical systems and used them to create the scientific and industrial revolutions. And I'll reveal how, in the 20th and 21st centuries, radical new theories are forcing us to question once again everything we thought we knew about maths and the universe.
The unexpected should be expected, because why would reality down there bear any resemblance to reality up here?
In this episode, I go back to the time of the ancient Greeks to find out where our fascination with numbers started.
You know, I think I can hear the neighborhood cats screeching.
And reveal why we're now looking for maths deep inside our brains. Our world is full of maths, often in unusual places, like this roller coaster.
The thrill and excitement of this ride wouldn't be possible without physics and engineering. And at the heart of all of that science is mathematics. Oh my God!
It's sobering to think how much we entrust our personal safety to maths without even realizing it. My rush of adrenaline relies on someone's calculations of kinetic energy, momentum, tensile strengths, coefficients of friction, and much, much more.
What do you make me do? To put it bluntly, the modern world wouldn't exist without mathematics. It is hiding behind almost everything that's around us and subtly influencing almost everything that we now do. And yet, it's invisible, it's intangible. So where does mathematics come from? Where do numbers live?
It's a question that goes to the very heart of our world. We often think about numbers as something tied to objects, like the number of fingers on one hand or the number of petals on a flower. This flower has got 8 petals. If I take 3 away, then it will be left with just 5.
and it will look a lot less pretty. The petals are gone, but the number 3 still exists.
The idea of 3, or any other number for that matter, is still out there, even if we destroy the physical object. But you can't say that about everything.
If pencils had never been invented, then the idea of a pencil wouldn't exist.
But the idea of numbers would still exist. In every culture around the world, we all agree on what the concept of fourness is like. And it doesn't matter whether it's called 4, 4, 4, or even what the symbol looks like. With numbers, I can destroy the physical object, burn it to a crisp. But I can't destroy the idea of numbers. So here's the question I want to answer.
Is it invented or discovered? Is there some magical parallel world somewhere where all mathematics lives? A place where you have fundamental truths that help us to understand the rules of science, helping us put man on the moon and to study the tiniest particles of the universe? Or is maths all in our minds? Is it just a figment of our imagination and intellect?
Whether maths is invented or discovered is something we can't agree on.
It's just too extraordinary to think that the mathematical truths and everything is a sort of product entirely of our conventions in the human mind. I think that's... I don't think we're that inventive.
It sometimes feels like mathematics is discovered, especially when the work is going really well, and it feels like the equations are driving you forward. But then you take a step back and you realize that it's the human brain that's imposing these ideas, these patterns on the world. And from that perspective, it feels like mathematics is something that comes from us.
The number 5 is called fem in Swedish, my mother tongue. That part we invent, the baggage, the description, the language of mathematics. But the structure itself, like the number 5 and the fact that it's 2 plus 3, that's the part that we discover.
There's virtually no part of our existence that isn't touched by maths. So if it is discovered, part of the fabric of the universe, how can we unlock its secrets? And if it's invented and all in our heads, how far can our inventive brains take us? I want to start with the discovered camp. Those who say maths is all around us. You just need to know where to look.
Of all of the structures that you get in nature, I think one of the most beautiful is the nautilus shell. So there's a little creature that lives inside here and creates all these shapes, and it hops from one chamber to the next as it grows. And this shell is just incredibly intricate. And you might wonder how something so small can create something quite so remarkable. But actually, there is a hidden pattern in here that you can start to see when you measure these chambers. So that one is coming out at 14.5 milliliters. And this one, on the same axis, is 46.7.
I'm measuring how wide the shell would have been as the Nautilus grew. I pick an angle and measure the inner chamber, and then a second measurement to the outer rim.
99.5.
I do this 3 times for 3 different angles until I have 3 sets of numbers.
When you look at them, I mean, they look pretty random, right? It looks like there's no connection between them at all. But looks can be deceptive because if you take each of these pairs of numbers and divide one by the other, a very clear pattern starts to emerge. So here, if we do this number divided by this, we get 3.22. This number divided by this one gives 3.25. 5, I think. Sorry, my mental arithmetic isn't great. And this number divided by this number then gives 3.24. And suddenly, the same number starts to appear, around about 3.2-ish. It doesn't matter where on the shell you measure, the ratio of the width of these chambers ends up being pretty much constant throughout the shell.
I've got it right to 1 decimal place. Not bad. That'll be down to my measuring skills rather than the Nautilus.
What all of this means is that the Nautilus is growing its shell at a constant rate. So every time it does a complete turn, it ends up sitting in a chamber that is around about 3.2 times the width of the turn before. And by repeating this very, very simple mathematical rule, it can create this beautifully intricate spiraled shell. Clever old Nautilus.
The Nautilus isn't the only living thing that has a mathematical pattern hidden inside it. If you've ever counted the petals on a flower, you might have noticed something unusual. Some have 3 petals, some 5, some 8, some 13, but rarely any of the numbers in between. These numbers crop up time and time again. They seem random, but they're all part of what's called the Fibonacci sequence. You start with the numbers 1 and 1, and from that point you keep adding up the last 2 numbers. So 1 and 1 is 2, 1 and 2 is 3, 2 and 3 is 5, and so on. When looking at the number of petals in a flower, these numbers from the Fibonacci sequence keep appearing. But that's just the start. If you look at the head of a sunflower, you'll see the seeds are arranged in a spiraling pattern. Count the number of spirals in one direction, and you will often find a Fibonacci number. Then if you count the spirals going in the opposite direction, you'll hit upon an adjacent Fibonacci number. Why do plants do this? Well, it turns out that this is the best way for the flower to space out its seeds so they don't get damaged. We find these spirals so intriguing, we've worked hard to unlock their secrets.
We've gotten very good at copying the patterns that we find in nature and using them to create things of great beauty, like this majestic staircase.
Simple, glorious mathematical rules found hidden in nature. Doesn't seem to me like a coincidence. These mathematical patterns, once you spot them, do feel discovered. It's as if the maths is already out there, just waiting for you to find it. This fascination for finding hidden mathematical patterns is nothing new. Go back over 2,000 years to the time of the ancient Greeks, and you will find the philosopher Pythagoras and his followers were just as enthralled by the patterns they discovered.
The Pythagoreans were obsessed with numbers. They were a people who believed that numbers were a gift from God. And part of their fascination might have been thanks to their experiments with music.
The Pythagoreans discovered patterns that linked the sound of beautiful music to the length of a vibrating string. This, they believed, was no accident, but a window into God's world that had been gifted to the Pythagoreans. Mathematician and musician Ben Sparks is fascinated by this age-old relationship between music and maths.
Thank you for joining us, Hannah, with your beautiful cello there. Okay, Ben, you are, you're going to have to explain this to me. Where does the maths come in making this instrument sound nice?
The wobbling is what's giving you the sound, and if you make the string wobble, you hear a sound. So maybe you could play your D string.
Oh, sounds lovely.
It sounds lovely, doesn't it? And what they also notice is another note really related to that, which is if you make it wobble twice as fast, and to do that, you can make the string half the length.
Okay, so you're putting your finger here, well, I guess pretty much is actually halfway along, okay.
What's weird about these two notes is they sound kind of the same, but they're definitely different, and this is what the Greeks noticed. We call it an octave.
But if you play them together, does it sound nice? It's delightfully pleasant.
In the octave, the length of the vibrating string creates a relationship or ratio of 2 to 1.
So that's if you chop it in half. Are there other fractions that make it sound nice?
Well, exactly what the Greeks were thinking. It was like, well, can we find other notes that sound even nicer together, more interesting together? Can you play us? This is what they call a perfect fifth.
What happens when you play those two together then? Very pleasant. I feel like we're about to launch into a jig there.
In a perfect fifth, the ratio of the vibrating string is 3 to 2. The high note is 2/3 of the length of the low note.
What happens when you play a note that isn't one of these neat fractions?
When notes aren't in these nice, simple ratios, we tend to notice it even if we're not aware of the mathematics, right? I mean, could you play a sort of really horrible harmony together? Maybe like a semitone apart.
When the strings are not in a simple ratio, the harmony sounds distinctly unpleasant.
The Greeks were obsessed with having simple ratios describing the notes, so they get nice, harmonious noises.
How does this work for other instruments? I mean, this is very clear. You've got this sort of string here, but what about, I don't know, like the human voice?
Right, well, every noise you ever hear is things wobbling somehow, whether it's your vocal cords or a string or...
Not my vocal cord.
Well, really, have you never used your vocal cords for a bit of music? Can we try?
Oh, no. I'm such a bad singer. Please don't make me do this.
OK.
Have you got your earplugs in?
Let's try. Can you pitch us a note? I mean, there's something nice and low. If you just do it to La, then I've got a chance at copying.
All right, okay. La.
Just like the cello, it's the length of mine and Ben's vocal cords that's changing the pitch of these notes.
So that was me singing a perfect fifth.
Uh-huh.
This Jarrett Sophia note, la, la.
You know, I think I can hear the neighbourhood cats screeching, so I think that's enough of that.
These patterns convinced the ancient Greeks that they'd been gifted a glimpse into this godly realm. Why else would these patterns exist?
Pythagoras and his followers were in little doubt. The maths was just as real as the music was, and it was even neater and more elegant than anything the human mind could conceive of.
The Pythagoreans were by no means the first people to use some form of maths. There's some evidence that marks found cut into bones from the Upper Paleolithic era, 37,000 years ago, were tally marks used for counting. But it was the Pythagoreans who were the first to look for patterns. It does feel to me as if maths is all around us and something we discover, a fundamental part of the world we live in, and yet somehow very strangely separate from it. Trying to make sense of this apparent paradox is at the heart of this battle about where maths really lives. The philosopher Plato is one of the most important figures of the ancient Greek world. But what he said about the origins of maths is still the basis for what many mathematicians believe today. He was fascinated by the geometric shapes that could be produced by following the rules of mathematics. rules that he believed came from God.
I'm going to try and draw a circle really, really carefully. Takes me back to my school days, this. Now, I'm not doing bad. That's pretty good. But if you look really closely, it's just not quite perfect, the circle. But I'm not going to beat myself up about this, because even if I had access to the most accurate computer in the world, the circle that it would draw still wouldn't be perfect.
Zoom in close enough, and any physical circle will have bumps and imperfections. That's because, according to Plato, flawless circles don't exist in the real world. He believed the perfect circle lives in a divine world of perfect shapes, a kind of mathematical heaven where all of maths can be found, but only if you're a true believer. He was convinced that everything in the cosmos could be represented by 5 solid objects, known as the Platonic solids.
So the Earth was the rock-solid cube, fire was the very pointy tetrahedron, and then with 8 triangular sides, air was the octahedron, while the icosahedron, with its 20 triangular sides, represented water. The last Platonic solid, the dodecahedron, this one was supposed to encapsulate the entire universe. It's the whole universe sitting in your hands there. It's kind of a neat idea.
There's something special about the Platonic solids. They're the only objects where every side is the same shape. And there are only 5. Try as you might, you will never find another object with these unique mathematical qualities. All of these shapes, Plato believed, existed in a world of perfect shapes, beyond the reach of us mere mortals, a place we call the Platonic world.
I know that these ideas might seem like they're a bit bonkers, but there are actually quite a few people who believe them, and those people come across as though they're sane.
Oh, my third most favorite mathematical structure, the octahedron.
Aha! The Platonic solids, I presume.
It's a dodecahedron. I love dodecahedra. I have a misspent youth making models of polyhedra.
Oh my goodness. These are the Platonic solids. Oh, guys.
Okay, very beautiful.
You know, at 67, this is Christmas.
Can I keep these 2, please?
These Platonic solids, to me, are a great example of how mathematics is discovered rather than invented. Because when ancient Greeks discovered that this one existed, they were free to invent the name of it. They called it the dodecahedron, but the pure dodecahedron itself, it was always out there to be discovered.
I have this kind of Platonic view that there are triangles out there are numbers, there are these circles that I'm seeking to understand. So for me, they feel like quite tangible things. They're all part of this mathematical landscape that I'm exploring.
But not everyone believes in this Platonic world of mathematical truths.
I think that the Platonic world is in the human head. It's a figment of our imaginations.
I get that there are people who really buy into this other realm of reality, and especially if your days and nights are spent thinking about and investigating and researching this realm, that doesn't mean that it's real.
Plato would have strongly disagreed. He encouraged us to believe in this other world, where all of maths could be found, and not to be fooled into thinking the world around us is all there is. What we perceive as reality, he cautioned, is no more than shadows cast on the walls of a cave.
Plato had a very lively and quite dark imagination. To explain what he meant, he came up with an analogy of a group of humans locked in a cave. These people would have been imprisoned since childhood, and they were shackled by their necks and their legs and trapped staring at a blank wall directly in front of them.
In his mind's eye, Plato pictured a fire burning high above the prisoners' heads. But they have no idea it's there.
On top of the wall is a path along which all manner of people and objects are travelling. But the only thing the prisoners can see of them is the shadows they cast down the wall. Those shadows are the prisoners' reality.
According to Plato, we're no different to the prisoners in the cave who mistake the shadows for reality. If Plato is right, what does this mean for you and me? Is what we think of as reality and maths just an illusion?
Are we living in Plato's cave and just see shadows? It is not impossible that that is the case. You know, we are maybe we're just some simulation in some world of some more intelligent being. This is all possible.
I mean, if you think that there's some world of mathematical objects, it's different from ours. It's not the physical world we live in, but that doesn't make the physical world any less real. So I don't think that there's anything to me in philosophy of maths that would force you to think that our world is an illusion of any kind.
Our senses evolved really for one purpose, survival. But survival and the true nature of reality are two different subjects. So the fact that we have been able to survive by thinking about the world one way does not in any way say that that way of thinking about the world is truly what's happening out there.
Over 2,000 years ago, Plato took the geometry of shapes as evidence of God's influence. Ideas that were limited to the senses and imagination. Today, geometry is at the cutting edge of science. New technologies have allowed us to look at the world beyond our senses. And once again, it seems the natural world really is written in the language of maths. This is a model of a virus. Straight away, you notice its geometric shape. Plato would have recognized this shape as one of the Platonic solids. If there's one person who understands geometry, it's a mathematician. Ryden Twarok is a professor of mathematics at the University of York. She's trying to work out how viruses use maths to form their geometric shapes. If you know that, you can find a way to stop them. That's why Ryden and her colleagues have designed a computer simulation that puts the mathematician at the heart of the virus.
What we try to understand is how this virus forms, and in order to do that, we will create the illusion of being inside of the virus in the position where the genetic material normally is.
Ryden has discovered that the virus harnesses the power of maths to build its shell in the quickest and most efficient way possible. Armed with this knowledge, she's trying to find a way to stop viruses such as hepatitis B and even the common cold from developing in the first place.
Once you understand how this mechanism works, you can turn tables on viruses and actually prevent that process.
That is what makes this research so exciting. If you know the mathematics of how the virus forms its shell, you can work out a way to disrupt it. No shell, no virus, no infection. Today, mathematicians like Ryden are joining the front line in the fight against disease. Far beyond the realm of human senses, it really does seem like the universe somehow knows maths.
It really is amazing how often these patterns seem to crop up. They're in plants, they're in marine life, they're even in viruses. There really is an awful lot that we can explore and exploit using the mathematics that we have.
it does lend weight to the idea that there is some natural order underpinning the world around us.
So far, it does feel like the idea that maths is discovered is leading the charge. But perhaps we've been looking for patterns in the wrong places. If it's all in our heads, then the brain feels like a good place to look. Is there evidence in there of maths being an invention of the human mind?
I've got a real treat in store for me today. I am heading over to UCL, the university that I work at, where some colleagues are going to scan my brain and see which bits of it are working whenever I do mathematics.
Neuroscientist Professor Fraj is going to place me inside an fMRI scanner.
So if you just put your feet up, please.
He'll measure my brain activity by tracking where the blood flows when I'm answering questions ranging from language to maths.
Okay, how is that? Right? Excellent.
If my brain treats the mathematical problems in the same way as any other problem, then it suggests there's nothing special about maths. It's the same as any other language. A clue, perhaps, that it's an invention. I'll have 10 seconds to think about each question. I don't need to answer out loud. I just have to work out the answer in my head.
Okay, Hannah, how is that?
Good. Some of those questions are really hard.
Well, we didn't want you to relax in there, really.
I've answered all the questions to the best of my ability. After a few hours of processing, Professor Sophie Scott has my results.
Is that my brain?
That's your brain.
Let me make sure I understand what I'm seeing then. Okay, so this is like you've cut my brain in half.
Yes.
And I've got the left-hand side there, is that right? And the right-hand side is that. So it's like you've chopped my head down the middle and then split it out.
Exactly. So what you can see here, Hannah, is the pattern of activity in your brain when you're hearing straightforward language. And here you can see, in the left hemisphere, very classic language areas activated.
The bright yellow areas are where there's increased blood flow, an indication that the neurons in the left-hand side of my brain are working harder. This is a side of the brain that we know is linked to language. Compare that to the right-hand side of my brain where there's hardly any yellow areas, which means there's far less activity taking place.
So can we see maths, please?
Oh, hold on. But this
and look
whole
at that.
bit here.
Yeah.
That's
and
so...
also down at the bottom there.
This time, when I'm thinking about maths, there are yellow areas in the right-hand side of my brain. This is very different to the lack of activity seen when I was thinking about language. These scans reveal there seems to be a place in our brains where maths lives.
What we're definitely able to say is this is not just the meanings of the words that you were reading. We're not just looking at you thinking about the meaning of words. You're seeing actually something that does seem to be qualitatively different for the maths.
Maths is real.
Maths is real.
At least in my head.
Yes.
I tell you what really struck me about that conversation with Sophie just then is that it doesn't matter whether you're doing 2 + 2 = 4 or whether you're answering these much higher level maths questions. It's the same bit of your brain that's doing the grunt work. It's not the same thing that does words or language. You're seeing these problems and you're manipulating them in your mind.
Research with similar experiments shows it's broadly the same for all of us. In your brain and mine, there is a specific place where we do maths. But this doesn't prove that maths is something we discover. It could still be an invention, just one that we learn at school. To get to the bottom of this question, I need some volunteers who've never had a maths lesson in their lives.
You need to just put one of those on there. Very nice. That worked very nicely, didn't it? Yeah, you like that, did you?
Dr. Sam Wass is an experimental psychologist at the University of East London. Helping him with some experiments are 6-month-old Ira and Leo, who's just under a year. To begin with, each child is placed in a room where they're shown a series of images. Sam uses a battery of tests to analyse how they react to different situations. The first experiment uses eye-tracking technology to see how the baby follows the movement of a piggy puppet.
Is that good?
So here we can see a feed out of what the child is looking at, and those 2 red dots are where the baby is looking. What we're presenting is a puppet that jumps up and then disappears. And it jumps up and disappears 2 times in a row, and then it stops. We present this same sequence again and again. And as the baby watches it again and again, their looking times, the amount of attention that they're paying to the screen diminishes. And that tells us that the child has learnt this sequence.
Now, instead of popping up twice as expected, the puppet appears 3 times.
Does the child notice the difference between the 2-ness of it popping up twice in a row and the 3-ness of it popping up 3 times? And if it does, then that tells us that the child understands the difference between 2 and 3.
These tests reveal that the child is surprised when the puppet appears more often. When larger scale experiments were carried out by researchers in the US, the results suggested that infants do have a sense of quantity.
So this research is really important because it suggested that even infants as young as 5 months old can do the basics of addition and subtraction. They know the difference between 1 + 1 = 2 and 1 + 1 = 1, which is an incorrect conclusion. And that, though, is a really, really strong, provocative finding. Yeah, this idea that the concept of mathematics and the basics of mathematics rules might be hardwired, might be innate in our genetic code.
This research isn't conclusive, but it does suggest we all come pre-programmed to do maths. Some argue that we evolved this maths part of our brains to discover the world of mathematical truths. The evidence for maths being discovered is compelling. We found patterns in nature. The latest technology has uncovered startling patterns in viruses, and scans reveal there's a part of our brains where maths lives. But this question is too important to leave the evidence here and move on. If it is discovered, if it lives in this other world, can we trust what it's telling us?
How do we know that our idea of numbers is right? How do we know someone isn't just going to come along at some point and say, well, actually, you've got that completely wrong, and 1 + 1 doesn't equal 2 after all? How do we know that we can rely on the maths that we take for granted?
What you need to be sure of is your foundations. If they're shaky, then all of your carefully constructed ideas come crashing down. And there was one mathematician who understood this only too well. His name was Euclid. Around 300 BC in Alexandria, he wrote one of the most famous and important books of all time, The Elements. He was trying to go right back to the beginning, to find the smallest elements on which you can build the vast, gigantic structure of mathematics.
If you have a little flick through, you can see the kind of things that Euclid was considering. So here it says that you can draw a straight line between any 2 points, which seems blindingly obvious. And here it says that all right angles are the same. Now, these are quite simple concepts, but I think that they really illustrate just how exhaustive Euclid had to be to build the foundations for what was to come.
He took statements like these, which mathematicians assumed were true, and put them to the test. He then set out to prove a whole host of other theories based on these fundamental building blocks.
This was really the first time that someone had written down formal proofs for mathematical assumptions. Now, mathematical proof isn't like scientific proof or proof in a court of law. There's no room for reasonable doubt here. Instead, if something is true mathematically once, then it is true forever. And that is why this book is so important.
It's the reason why Euclid's Elements is still relevant today. Every page within it is as true now as it ever was.
And from that point of view, it really does feel like we're tapping into a world that already exists, one that's just out there waiting to be discovered.
Unless, of course, you throw a spanner in the works. Change the language of maths and invent a better way of doing things. Suddenly, this rock-solid world of God-given truths might feel decidedly shaky.
1, 2, 3, 4, 5. Well done, good counting. Muy bien.
One thing we know about languages is that they never stand still. They're constantly evolving to meet the challenges of a changing world.
47. 49. Muy bien. Let's go for another tricky one.
For centuries, the language of maths was thought to be fixed and unchangeable. That is, until something was found to be missing.
It is the number 0.
What exactly is 0?
A 0 means nothing. If you've got 0 flowers, you've got no flowers. And if you've got 0 of something, you've got nothing. So you can't really do anything with the 0. I don't really use it when I'm counting in numbers.
Before the 7th century, neither did anyone else. Though people have always understood the concept of having nothing, the concept of 0 is relatively new. We had numbers and could count, but 0 didn't exist.
If you think about it for long enough, 0 is actually quite a strange concept. It's almost as though the absence of anything becomes something. Is it just a number or an idea? And how can something with no value have quite so much power?
It's not exactly clear who first thought of 0. It might have originated in China or India. What we do know is that 0 arrived in Europe from the Middle East at about the same time as the Christian Crusades against Islam, when ideas coming out of the Arab world were often met with suspicion. The West already had a numerical system, Roman numerals. They did the job, but were a bit unwieldy. For example, the number 1958 is written as MCMLVIII. And no matter where you place, say, the letter C, it will always represent the number 100.
It was good for its time, but times change, and a better system was needed.
0 was different. Where you place 0 could change the values of the numbers around it. Think of the difference between 11 and 101. Although the concept of 0 might have been created elsewhere, it was in India that 0 started to be accepted as a proper number. This is a page from the Indian Bakshali manuscript from around AD 225, which shows the dots above the characters representing 0. This is the earliest known use of the symbol 0 that we know today. For almost 1,000 years, Indian mathematicians worked happily with 0, while their Western counterparts ploughed on with the Roman numerals. That was until Italian mathematician Fibonacci recognized its potential.
Now, he'd been educated in North Africa, so he'd seen this number system working firsthand.
0 is a placeholder, signifying the absence of a value. 0 is also a number in its own right. It allowed you to write down numbers and manipulate them much more quickly and easily than Roman numerals. Realizing all this, Fibonacci champions the new number and brought it to the attention of Western Europe.
0 wasn't something that we discovered so much as something that was created as part of a new language to describe numbers. And that's not to say it isn't useful. The whole of modern technology is literally built on ones and zeros. But suddenly maths feels like something we've come up with, something we've invented.
We needed a more user-friendly numerical system, so someone came up with the clever idea of 0. Not a gift from the gods, but a smart way to make counting more convenient. This is intriguing evidence that maths might be invented after all, a product of our intellect and imagination.
Once the idea of 0 had been widely accepted, mathematicians could relax. All conceivable numbers lay out on a single line with no holes and no gaps to speak of. Over here you have the positive numbers, 1 sheep, 2 donkeys, the kind of stuff you find in real life.
And in the other direction, all the negative numbers. It's a bit trickier to imagine what -1 sheep looks like. The number line stretches out in both directions all the way to infinity.
And 0 sits proudly in the middle. Everything was well in Numberland, or was it?
This is where it all starts to get a bit strange, because there are some numbers that are simply weird.
There are some fundamental rules of maths that you learned at school. 2 times 2 equals 4. 3 times 3 equals 9. A positive number multiplied by itself equals another positive number. Nothing controversial so far.
Curiously, a negative number multiplied by itself also gives a positive number.
Why is that? Well, this is not a maths lecture, so let's just accept it as a fact and move on.
In fact, if you take any number and multiply it by itself, or square it, then the answer is always going to be positive.
If +2 squared gives me +4, and -2 squared gives me +4, what do I have to square to get -4?
But it's a question without an answer. There is no number that when multiplied by itself gives a negative answer. That is, unless you invent your own. Meet I, a number we simply made up.
Not everyone was keen. It became known as an imaginary number, a deliberately chosen derogatory term to scoff at its existence.
It turns out I is really useful, especially when it comes to simplifying problems with things like electricity or wireless technologies, things that otherwise would seem impossible to solve. Essentially, if you're working with waves, you will use I. This imaginary number broke all the rules. It didn't come from this world of ethereal numbers. It wasn't God-given. It was very definitely invented.
If you can have one imaginary number, why can't you have 2? Or 3? Or infinitely many of them? Why can't you have negative imaginary numbers as well? Why can't, in fact, imaginary numbers have their very own number line? Exactly the same as the real one, just on a different axis. The number line isn't a single line at all. Numbers are 2-dimensional.
You might think this all sounds a bit airy-fairy. Imaginary numbers that we just made up. But if you've ever flown in an aircraft, you've already trusted your life to these strange numbers.
After BA3 4811, so 2239 Juliet Charlie behind the landing 737 at 3 miles per hour for 3.
At Gatwick Airport, air traffic controllers here rely on radar to keep everything moving safely and quickly.
Once you get busy, you definitely need radar. So the busier the tower, the busier the operation, you need radar.
Radar works by sending out radio waves and examining that part of the signal that's reflected back. The complex equations that allow us to filter out the correct signal from other conflicting frequencies is heavily dependent on imaginary numbers. In this case, separating out moving objects like planes from flocks of birds or stationary objects.
Imaginary numbers are a very efficient tool to be able to manipulate radio waves. Imaginary numbers are fundamental to the operation.
Imaginary numbers allow us to track planes in real time. Without them, we never would have been able to use radar in our skies.
Easy 29 Fox Bravo, thanks. Straight ahead there, just hold short of taxiway, Papa. Straight ahead, hold short of Papa, easy 29 Fox Bravo.
When I started this investigation going back to the time of the ancient Greeks, it did seem like maths could only be discovered. There were too many coincidences, too many mathematical patterns popping up all over the place. But if we can invent the rules, create new numbers, and they work, then perhaps I've got it wrong. Maybe maths is invented after all.
The concept of zero or negative numbers or complex numbers or imaginary numbers, they cause great consternation to the cultures that first invented or encountered them.
There are some conjectures that zero came because someone constructing noticed that as you dig a piece of earth out to make a hole, there's something, an indentation left there. That should have a name. Zero kind of maybe came from that observation.
The power of mathematics lies in the way its language and symbols have allowed us to manipulate the world. But this was a world that followed the rules of God and the Church. By the 17th century, a new breed of intellectual was emerging, not afraid to challenge authority.
There was one man who dared to question all of the philosophical and scientific assumptions that had gone before. This was someone who was trying to promote a new way of thinking, using reason, experimentation, and observation. This was the young Frenchman called René Descartes.
It was while in a restless sleep in 1619 that Descartes experienced a series of dreams that would change his life and mathematics. The first two could be better described as nightmares.
But the third dream was intriguing.
As his eyes scanned the room, he saw books on the bedroom table that appeared and then disappeared. He opened one book of poems and at random caught the opening line of one, which read,
"What road shall I pursue in life?"
Then someone appeared out of thin air and recited another verse, saying simply,
"What is and is not?"
As with dreams, it's all about the interpretation you place upon them. In Descartes' case, the effect of these dreams was profound.
He was convinced that the dreams were pointing him in a single direction, bringing together the whole of human knowledge by the means of reason.
He was nothing if not ambitious, but his genius led to perhaps one of the greatest advances ever in the field of mathematics. As with so many brilliant ideas, it was deceptively simple.
Let's say that I'm meeting a friend for a coffee. Now, I'm standing at the end of Ensley Gardens, and they are somewhere over on Gordon Street. It's very easy for me to work out how to get there. All I need to do is go on a map and check the route.
In this case, 3 streets down and 1 along.
It sounds like an incredibly simple idea, but actually, it revolutionised mathematics.
He showed that a pair of numbers can uniquely determine the position of a point in space. It sounds trivial, but this was just the start. It gets more interesting when you apply this idea to curves. As this point moves around a circle, its coordinates change, and we can write down an equation that precisely and uniquely characterizes this circle. For the first time, shapes could be described by a formula. By uniting the language of numbers and equations and symbols with shapes, Descartes was able to expand the horizons of mathematics, thus laying the foundations for the modern scientific world.
What Descartes and the other trailblazers like him did was to question the accepted wisdom of the time. They thought differently, and the result was that they delivered monumental breakthroughs for our understanding of the universe.
Descartes lived in a time when many philosophers backed up their arguments with appeals to God. But Descartes preferred to place his trust in the power of human logic and maths. He believed all ideas should have their foundations in experience and reason, rather than tradition and authority. It still feels like maths belongs to a discovered world, but after Descartes, it's a world that is increasingly devoid of a divine influence.
We started this episode with just one question: is mathematics invented or discovered? And based on the evidence so far, I'm leaning quite heavily towards discovered, because it doesn't seem to me to be possible that something so all-encompassing could be the product of the human mind alone.
Next time, I see how new mathematical systems allowed Newton to create his laws of gravity, and even started describing the existence of things we didn't know were there. All more evidence for maths being a discovery.
Now, this couldn't be a coincidence.
But I'm forced to think again when I confront one of the strangest mathematical concepts there is: infinity. And it makes the question of whether maths is invented or discovered a lot more difficult to answer.
What makes our world work the way that it does? Explore more about the magic and mystery of mathematics and how it impacts our everyday life. Just go to bbc.co.uk/maths and follow the links to the Open University.
And Hannah returns next Wednesday at 9. In the meantime, she's with Adam Rutherford, investigating everyday mysteries from pain thresholds to déjà vu. The Curious Cases of Rutherford and Fraj on iPlayer Radio. Tomorrow here on BBC4, Brian Cox marvelling at our place in the great scheme of things. Human Universe at 8.